Hello class, welcome to the next segment in lecture 16, and in this segment we're going to introduce the idea of ageostrophic wind and see what that means for us in the atmosphere and with our conception, how that affects our conceptual model of the atmosphere. So let's go ahead and dive right into it. So the whole idea behind ageostrophic wind kind of stems from the fact that geostrophic wind doesn't always represent the actual wind that we observe in the atmosphere. And to a good approximation, geostrophic wind can often model the actual flow pattern in the atmosphere, but there's always going to be some component of the wind that is not geostrophic. And that's the component that we often refer to as the ageostrophic wind. So the actual wind in the atmosphere is composed of a geostrophic component, which is typically the most prominent, and an ageostrophic component, which is usually at any given point in the atmosphere is typically weaker, but it can be something that we have to worry about. So represented mathematically, we can state that the actual wind in the atmosphere, V, is equal to a geostrophic component, V sub G, plus a non-geostrophic component, V sub A, and this is often referred to as the ageostrophic component of the wind. So the reason why I said non-geostrophic is because I'm trying to highlight the fact that this component of the wind is not a geostrophic component. It's if the atmosphere were purely geostrophic, then the actual wind would exactly equal the geostrophic wind, but uh, and strictly speaking, the atmosphere is never perfectly geostrophic and can be approximately geostrophic, but it's never perfectly geostrophic. So there's always this non-geostrophic or ageostrophic component that's present in the atmosphere somewhere. Now, using this definition, we can also tie this to our equation of motion that we've been working with in the first part of the class to sort of get an idea of where exactly this ageostrophic wind represents. Where is it present, and where might it be negligible? So we're going to take a look at the equation of motion, but we're only going to consider two forces here. We're only going to consider the two forces that would impact geostrophic balance. So we're only going to look at pressure gradient force, which is this minus grad phi, and then we're also going to look at the Coriolis force. And notice I'm using the total wind vector here. I'm not using the geostrophic balance. I mentioned the forces involved in geostrophic balance, but I'm going to assume there is not a balance here. So we're going to assume that this term on the left-hand side is non-zero. We're going to account for the possibility that there might be some sort of acceleration to our flow pattern. So here we're neglecting centrifugal force as well as friction. Also, momentum advection is being neglected here. So if those three forces, any of those three forces is strong, then this idea of ageostrophic wind won't work particularly well. So just something to keep in mind. Here we're still assuming a mostly straight flow pattern, but this will give us a better idea. This will actually be useful to us when we go to explore the idea of jet streaks, which we'll talk about in the next segment. But here, we can use the idea of geostrophic balance to substitute in an expression for this pressure gradient force, this minus grad phi. So you may remember from lecture 6 when we introduced geostrophic wind that we end up with an equation that looks like this. The pressure gradient force is equal to the Coriolis force. And if we take this expression for minus grad phi and substitute this expression into this equation up here, we get an equation that looks like this. So we have this F k hat cross V sub G minus F k hat cross V, geostrophic wind, actual wind, and then also actual wind over here on the left-hand side where that time derivative is. And one of the nice things about cross products is we can use the distributive law just like we would with any other scalar product or any other multiplication, and we can rewrite this equation like so. We can get dV dt is equal to F k hat cross geostrophic wind minus actual wind. Now we can use our definition that we started with earlier. The actual wind is equal to the geostrophic wind plus ageostrophic wind. And if we rearrange this equation a little bit, so we can get something that looks like actual wind minus geostrophic wind is equal to the ageostrophic component of the wind. And if we put a negative sign into both sides of this equation, we get that the geostrophic wind minus the actual wind is equal to negative times the ageostrophic component of the wind here. And if we take this result, Vg minus V is equal to minus Va, we can take that and substitute into the equation that we have up here to get that dV dt is equal to minus F k hat cross ageostrophic wind, or ageostrophic component of the wind. And if we want to solve for the ageostrophic component, we go through a similar procedure that we did with geostrophic wind, where we have to k hat cross both sides and employ that nifty little vector identity. And when we do that, we get something that looks like this, So again, k hat cross some vector is just equal to the negative of that vector. Negative of that vector times negative f results in a negative sign that cancels out. And then here we just simply divide f over to the other side of the equation, and we get that the ageostrophic wind is equal to 1 over f k hat cross dv dt. And if you think about the definition that we gave for geostrophic balance way back in lecture 6, this actually makes sense because in geostrophic balance, we're assuming that the acceleration is 0. And if our wind is purely geostrophic, then there is no acceleration to the wind at all. But if we've got an ageostrophic component to our wind, then this equation tells us that there might be some sort of acceleration involved. So in the case of a purely geostrophic flow pattern, there's no acceleration, the ageostrophic wind is 0, and the acceleration is 0. But now we've got a term that can actually account for any accelerations that might be present, and the acceleration is only related to ageostrophic wind. There's no relationship between acceleration and geostrophic wind. Any acceleration in the flow must be due to the ageostrophic component in the wind, that is, the component of the wind that is not in geostrophic balance. And just like any other cross product, we have a right-hand rule that we can employ. So just like with all the other cross products that we've looked at, the thumb represents the first vector in the cross product, which is k hat, which points directly upward. The index finger points in the direction of the acceleration vector, and to get the ageostrophic wind, we just simply look where our middle finger is pointing when we go to employ the right-hand rule. So we'll actually apply this in the final segment when we take a look at jet streaks. That's when we're going to start applying this information to a real-world situation. But I do want to go ahead and cover a few other points about ageostrophic wind, and one of those points has to do with the divergence of the ageostrophic wind, or the divergence of the wind field. So if we take this above equation right here and apply a divergence operation to both sides of it, so del dot total wind on the left-hand side and del dot geostrophic wind plus ageostrophic wind on the right-hand side. And again, just like any other product that involves vectors, we can use the distributive law to get a result that looks like this. So divergence of V is equal to divergence of geostrophic wind plus divergence of ageostrophic wind. And something that you may recall proving in your second homework is the fact that the ageostrophic wind is non-divergent, or stated mathematically, the divergence of the divergence of the geostrophic wind, del dot V sub G, is equal to 0. So if this term is equal to 0, that means we're left with something that looks like this. The divergence of the wind field is equal to the divergence of the ageostrophic component. Now what this tells us that any divergence or convergence in the wind field must be solely due to the ageostrophic component of the wind. So if we have a purely geostrophic flow pattern, that means there's no divergence or convergence present in the atmosphere. But if we do have convergence or divergence of some sort in the atmosphere, then that must be due to some sort of ageostrophic component in the wind. You can't have divergence or convergence if you don't have some sort of ageostrophic component in the wind. And this actually works out kind of nicely because here we only need to worry about what direction the ageostrophic wind vector points to diagnose divergence or convergence, and we can calculate ageostrophic wind vector if we know how the wind is accelerating. So and we'll actually apply this specific concept in particular, to the next segment when we talk about jet streaks. But again, I want to reiterate an important point here. This whole idea that we're working with only works well if we got an approximately geostrophic pattern. So it's really hard to make a good case for this particular equation if you've got strong curvature in the flow, if you've got strong friction, or if you've got strong momentum advection. But one of the nice things is this ageostrophic wind kind of absorbs all those forces anyway. So if you've got curvature or friction, then the ageostrophic wind will kind of contain information on those specific terms. Although it might be really hard to calculate mathematically, it is something that we can estimate if we're observing the actual wind in the atmosphere. But that's going to do it for this look at ageostrophic wind. And in the final segment, we're going to take this concept and apply it to jet streaks, which is a locally strong current of air in the jet stream. So with that, I will see you all in the final segment.